All right. I hope that this is actually working. I've been having some technological challenges with this. So, this is going to be a shorter recording than I previously planned, and hopefully, I can do just another one after this to follow up with the rest of the assignment. So, we're just going to do a little bit since it's getting late at night here. Okay. Um, so, I'm in section 1 here of the most recent assignment on limited resources and competition. It's talking about the uh, fundamental niche versus, well, is starting to get the idea of what would limit the distribution of where an animal lives. And that's actually a pretty big part of ecology, is just trying to figure out why do things live where they live. And there's the fundamental niche, and then there's the realized niche. And the realized niche is always going to be smaller than the fundamental niche. So, for example, lions maybe could live in Texas, but they don't. Okay, so the constraints on where can lions live, well, there are probably a lot of places in the world that they could live that they don't. Maybe they could live in Australia and eat kangaroos, but they don't. Okay, so there are geographical barriers there, and that's one, you know, limit to the realized niche. And you can say niche, you can say niche. I tend to say niche, but in French, niche is a nest, and but in ecology, a niche or niche is just all the different variables that describe where something lives. And so this starts to look at temperature and humidity, but it could be soil type. It could be, what is the coldest cold of winter? Why are there, fire ants were introduced into the U.S. and they started to spread all through the South. Why haven't they spread too far north? It probably, they're limited by the coldest wintertime temperatures. Um, okay, so just the idea of fundamental niche versus realized niche. And I'm going to skip the simulations and skip, um, you basically you find some limiting factors. And, you know, it, if it's dry enough, the mosquitoes won't thrive, or if it's too hot or too cold or whatever. And they give some background with Joseph Grinnell and Charles Elton and Gauss. Um, and Gauss worked with paramecia, and he showed. Um, Let me see if I can I extend this. Just a minute. Let me pause. I don't even know where the pause is. Okay, the growth curves. I was trying to extend my screen over. Maybe I can do it this way. Aha! Look at that. Okay, so either one would reach carrying capacity on its own, but when you put both species together, um, one, the Paramecium aurelia, always won out against Paramecium caudatum. And basically, this idea that two species can't overlap completely in their niche and coexist. And in the case of these paramecia in the wild, they probably don't overlap completely. Maybe one specializes on one habitat or one type of food or something more than the other. Perhaps in the wild they can compete and live together, but in the simplified petri dish scenario here, where they had only one food source, you put them together and one of them wins out. Okay, so what we see is that even though things may not coexist in a lab setting, in nature they often do coexist, and so there are all sorts of other factors that play into it. So maybe the competitor, let me go back one. Maybe this Paramecium aurelia that is the winner. Maybe there's a predator that knocks its numbers down in nature and allows the caudatum to coexist with it. So, or a parasite or some other factor. Classifying competitive interactions. I know there was one question that somebody asked was interspecific versus intraspecific. And in this little scenario here, we're just looking at one type of shrub and it's competing with itself. Now, if you think about it, a species competing with itself, that's the most overlap. That's complete niche overlap, right? I'm a flat-tailed horned lizard, you're a flat-tailed horned lizard, we both do flat-tailed horned lizard things, right? We like the same habitats, we like the same foods, we like the same temperatures. We overlap because we're the same species. So if resources are limited, if that's the limiting factor, then competition can get severe. Now, oftentimes it's not a particular resource that's limiting, right? Because maybe our numbers haven't reached carrying capacity. So if we're talking about a lizard population, well, it may be that we never reach the carrying capacity of the environment. We don't run out of food. We don't run out of space because the predators keep our numbers down. So sometimes populations hit that carrying capacity, sometimes they don't. And if they're below carrying capacity, then competition might not be the limiting factor. So either in where they live or in their numbers, okay? So, what else have we got going here? Allelopathy, this is just plants putting out chemicals to inhibit competitors. So some plants actively, essentially poison the soil for others. Now, it doesn't poison it for themselves. That's the trick of it. Territoriality only applies to animals. Well, defending a territory, right? That's actively going out and defending it. That's only going to apply to animals. Preemption is just being the first on the spot. This could be animals or plants. So when there's a space open, being the first to fill that space. This even applies to business, right? When there's some new opportunity opens, if you're the first, then you have kind of a first mover advantage. Doesn't mean you'll be the one to last forever there, but it gives you some advantages. There's a creosote bush. And now, an interesting thing, if you drive through the southwestern United States, you'll see creosote bushes not just in dunes, but all over the place. This is the dominant plant all through Arizona and New Mexico and Nevada and parts of California. And we are at the edge of the creosote range. When you hit the Chihuahua Desert, suddenly it's not the dominant plant anymore. And it's actually quite rare around here. So is there something different about the fundamental niche? Is there some physical limiting factor for why it's not outcompeting things here? Maybe. Might be the pH of the soil. Maybe it does poorly with all the limestone. Or maybe it would survive here really well, except there's a stronger competitor under the current conditions. I don't know. I don't know what the limiting factor is for that plant in Texas. But trying to move quickly through here. That's a really bizarre picture. But this would be, so creosotes competing with other creosotes, that's intraspecific competition within the species. This really odd picture would be interspecies, two different species competing for the same food. Now, a starling and a prairie dog probably overlap very little in their niche, right? If you have 1,000 times more starlings, it probably doesn't really affect the prairie dogs too much. Or if you had 1,000 times more prairie dogs, it probably wouldn't affect the starlings very much. They probably have enough foods that each one eats that the other doesn't eat, that there's just not going to be much competition. So I wouldn't have. That's not a picture I would have chosen. But maybe deer and elk, or how do they overlap? How do they divide the niche? How do they avoid the competition? Or rabbits and deer, or things like that. Okay, moving along. Hopefully, if any of these terms don't make sense to you, just let me know. Trying to move here to the next chapter here. Modeling competitions. R equals B minus D. We start to get a little bit of math here, and I know that starts to worry people. Let me see, how do I... Here we go. R equals, so rate of growth equals birth minus death. This is the population rate of growth. And don't worry about, if it's per 1,000 or per 100 or per individual. Just that the population is growing if birth rate is greater than death rate. If death rate's greater than birth rate, then R is going to be negative. The population is going to be declining. And that happens, right? Populations go up and populations go down. That happens. Human population has been going up, 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 up. Now, the rate of growth has been declining, even though our population continues to get bigger and bigger, right? So if you think about it, women on average are having fewer babies now than 100 years ago, right? And there's a smaller percentage of women in the population that are even having any babies. And so the per capita growth rate is down. But we have so many more people now than we did 100 years ago that even with that smaller R, our population still grows quite quickly. We have been in an exponential growth phase for quite a while. And in terms of carrying capacity, a lot of people think that we've overshot our carrying capacity and that the population will come back down. We can talk about that a little bit. Okay, so this looks like the growth rate that we're on. If you map human population over time, you'll see that we are in this phase right here, the very, very high growth rate. So this is called exponential growth. And any population, elephants, can do the same thing given enough time. So the amount of time needed to demonstrate this is going to vary by species, but all species have the capability of doing this if they are not limited in their growth. Okay, if there's not some sort of limiting factor. Now, you can do this in the lab with like bacteria or paramecia or something, and something very fast growing, and you'll see that the population, it goes through a time when it seems to be growing slowly, and it's just because the numbers aren't there, right? 2 becoming 4, 4 becoming 8, 8 becoming 16. You're getting this doubling, but that doesn't seem to be doing much, comparatively. When you double 256 and you get 512, and then you get, 1,024. Where was I in this? 2,048. Okay, and now the doubling, you're at 2,048, and just one more generation of doubling, and you're over 4,000, 4,056 or whatever. And so it's the time span per generation hasn't changed. The doubling rate, the growth rate hasn't changed, but the amount of growth that happens in that same period is now much, much greater. And so, if you get up to 1 million, well, it took a long time to get to 1 million, but it takes a short time to get to 2 million. It takes as much time to go from 1 million to 2 million as it did to go from 4 to 8. And 4 to 8 is not even going to show up on this graph. If you're trying to plot, say this is 2 million, and maybe it was 1 million right here. So it went 1 million to 2 million, and that's the same as going from 4 to 8, same time period. So it looks flat, and then suddenly shoomp. So this is called exponential growth. Now, interesting, sometimes you'll see this on a logarithmic scale, and it will actually be a straight line on a logarithmic scale. indicating that the growth rate isn't changing. The rate isn't changing, even though the population size is growing faster. So that's a little confusing. The rate, the R being, that birth minus death, the per capita. So how many babies per 1,000 people or whatever hasn't changed, even though the effect is much bigger. Okay, moving along. Intraspecific competition in these mosquitoes. So intraspecific is just within the species, basically saying if it gets too crowded, that's going to affect growth rate, it's going to affect reproductive rate, and so on. And this is a density dependent sort of thing, that a whole bunch of them in a small area, they're going to use up the resources. Moving along. And survivorship. Okay. This is something to spend a little more time on, just because now we've got natural log, and I was like, what in the world? And you don't need to figure out, if you once understood logarithms and natural log, and you're like, oh, I want to understand that again because they're talking about it, good, go ahead and do that. If not, it's not critical that you understand what that means. You can just kind of go through the steps here. And so what are we trying to do here, though? We took we showed the population at day 0, at day 20. We divided the population of day 20 divided by day 0 population, and then we took the natural log of that and got a number, and then we divided that number by the number of days, by time, and we end up with R. Okay, now that looks different than births minus deaths. It's the same R, it's the same growth rate. It was accomplished in a different way. And nope, I'm not going to. If you want to see why that is, then I'll do another video if you want, or come visit me or something. We can work through it. But just know that it's the same thing. It's the calculating it this way. All you're doing in this instance is looking at how many did I have here, how many did I have later, and calculating R from that, as opposed to keeping track of, well, how many are being born, how many are dying, and which is a much harder number. It's hard enough to get a population estimate. It's even harder to get birth rate and death rate. But you're getting the same thing from these two sets of data. So what you're getting is R, the growth rate. Okay. K is carrying capacity. Now, carrying capacity just means we have this many resources. This is the population that we can sustain with this many resources. Now, the only thing I want to say about carrying capacity is it doesn't stay the same all the time. Okay, let's say we're looking at the carrying capacity of quail in Texas. So assume nobody in Texas hunted quail. Some years, there would be much fewer quail than other years. Why is that? Well, let's take away predation. Let's get rid of predators, humans, foxes, everything, and say, okay, only thing limiting quail is amount of food that they have. And in some years, it's going to rain at just the right time and in just the right amount, and the quail population is just going to way, way, way up. because they have a very fast growth rate, and so they boom, they hit, they just go way up, 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 up. Then it's possible to overshoot carrying capacity. If this is carrying capacity, it's possible to go past it, but then, dive under it. But let's assume that they match carrying capacity perfectly. So this nice smooth curve, they hit that. Well, the next year, it didn't rain at all. And so now there's this much food available. I mean, the carrying capacity really is here. The population's up here. The population is going to drive down. Okay, so maybe the population was here one year, and then the carrying K went up because there were more resources, and the population followed. And K went down, and the population followed. So K is not constant, really, and we don't really know where that is exactly. How many humans can this planet support? Are we at K? Are we over K? Are we, is K 12 billion? Is it 2 billion? It's actually very hard to tell. And all you can do is watch the population go up and down. And if it goes up and down, up and down, up and down, and it's always kind of tracking around here, and you say, well, that was K right there. So you can do this in the lab. You can do it in the lab, but in the wild, you can't really give a good number for what carrying capacity really is. But the idea just makes sense that when there are more resources, you can support a greater population. Okay. Now, I wanted to talk about this. dn over dt equals rn. This is the exponential growth equation. So if we, we get this exponential growth versus logistic growth. Okay, so this is a little confusing, I found, because let me move myself. Here it says exponential, but that's to switch to the exponential. That's the exponential growth curve. That's the logistic growth curve. What's the difference? Well, first, how do we even say this? dn over dt. D stands for delta. Delta n over delta t. What does that mean? Delta means a change. So delta is a triangle shape, Greek letter. And so they could have done that. N is the population size. Okay, N is population. T is time. Delta N is change in population. Delta T is change in time. So the change in the population over time. That's what this equation is about. How is the population changing over time? So over a time period, how's the population changing? Is this calculus? Yeah, I guess. Do we remember our calculus? No, probably not. What's calculus about? Calculus is about math of something that changes over time. Figuring out something that changes over time. So with this, the growth rate is constant. And you're just timesing that growth rate times the population size. So as population size gets bigger, a population of 50 times the growth rate, that's less growth than a population of 150 times the growth rate. So what's this side of the equation? How much did the population change over time? And so here, it's just as n gets bigger, the overall change in the population just goes up, up, up. Okay, so here we have a small n, and so our change in time, let's say over 2 days, this is something that's growing really fast. So let's say change in 5 days. Well, we didn't have much change. We went from 2 mosquitoes or something to 10 mosquitoes, or let's say about 10. Over the next 5 days, 10 times the growth rate, we went up to 120. In the next 5 days, we're off the charts. Okay, we're off the charts. So change in time, the change in the population over time. There's the growth rate, population growth rate, and there's the total population at any point in time. Now we add this. This puts a limit. Okay, and let's look at what that limit is. This is, as you approach carrying capacity, things are going to slow down. Why is that? Well, 1 minus, why do we have the 1 minus something in there? Let's look at this. If n is very small and k is very large, then it's going to be close to 0. Right? Let's say n is 1 and k is 1,000. Okay, so 1 minus 1 1,000th is basically 1, right? So 1 minus 1 1,000th is 0.999, right? 0.999. So this term times almost 1. So we really haven't changed this term. We haven't slowed the growth of the population at all. Now, if k is 1,000 and the population is now 100 over 1,000, that's 0.1. So now Rn times 1 minus 0.1 is 0.9. Rn times 0.9. Now we're at 90% of the potential growth rate of the population, right? And if n is 900 and k is 1,000, 900 divided by 1,000, that's 0.9. 1 minus 0.9 is 0.1. Okay, so what we've done as we approach k, as the population approaches carrying capacity, everything slows down, right? Because now we're taking the growth rate of the population and timesing it by 0.1. It's only 10% of what it could be. And why does it go flat like that? Because when n reaches k, 1,000 divided by 1,000 is 1. 1 minus 1 is 0. Rn times 0 is 0. The change in the population over time is 0. And that's what we see. The population is not changing over time. Dn over delta n over delta t, change in the population over time has hit 0. Now again, this is how it works with math. In reality, you're going to overshoot k, undershoot it, zig, 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 zag. It's not going to be nice, smooth, whoop, level off to an asymptote exactly. But hopefully that much makes sense now. And I apologize if I took too long to explain it, but that's delta n over delta t. That's our growth rate. That's our population size. The logistic growth is just adding in, slowing the growth down as you reach carrying capacity. And by definition, it stops, growth rates, the growth of the population stops at k with this math in there. Okay? And then you can see the difference, slow growth rate, fast growth rate. And this is with a carrying capacity. Now, if you have a slow growth rate and a high carrying capacity, we don't see reaching that carrying capacity on the scale of this graph. You'd still reach it. And if you have high growth rate, you just reach k sooner. It doesn't really matter the size of carrying capacity. You reach it quickly with a high growth rate. Okay, I'm going to stop there, I think. Mainly I wanted to discuss the logistic growth equation for now. And, these 3 points, the population is growing more and more slowly over time because of this part of the equation. Because it's reaching carrying capacity, right? And the human population is growing more slowly over time. But we're actually still on a very steep growth curve. We're still on the... Okay. Now I have to figure out how to turn this off. And I actually don't even see that. Stop. Stop, stop.